Hi there! Whether this is new for you or just a review, welcome back to the Fundamentals of Logic. This is part 5, so if you haven't seen our previous videos or studied some logic before, you might want to go and check those out first. In this video, we're going to continue looking at our method of syntactic logic. And after a quick review, we're going to start by looking at some examples of what we saw last time. Even though we've been looking at the mechanics of logic, it really is something that's meant to be used in the real world with real arguments. And so we need to look at how natural language sometimes makes it difficult to tease the premises out of an argument. But first, let's do a quick review. In our last video, we learned a process which we call syntactic logic, which allows us to add or remove connectives from our logical argument. These were called introduction and elimination rules, and these rules are important because they preserve truth. Remember that validity depends on a conditional being true, or rather, the conditional cannot go from true premises to a false conclusion. If something is true, we have to make sure it stays true when we get to the next step. Here again, we can see a summary of the rules we learned last time. Notice we've included the rule of iteration, which allows us to restate a premise, although it's more of an admin rule, really. Notice as well that 3 of the rules allow us to remove premises from the support column: the negation introduction, conditional introduction, and disjunction elimination. This is a very useful step which we will see come up a lot. We also talked about how we can assume new premises to help with our derivations. This is sometimes written as a separate rule of assumption, and these assumptions, or hypotheses, begin a subproof. The core of every argument is its premises, but not every premise is equally important. Sometimes we assume a premise just as a stepping stone towards our conclusion, but our argument does not rest on its truth value. These kinds of assumed premises are called hypotheses, and each hypothesis will start a new subproof. And the subproof is completed or resolved when we remove the hypothesis from the support column, and then we can move on with our derivation. Really, we only need to either track the subproofs or record our supporting premises. You can do both in our table form, but if you get to be good at these derivations, you'll probably develop your own shortcuts for going through them. But when the time comes to write out your argument so that someone else can understand it, then however you do it, you must be as careful as possible to show that each of your steps is correct and truth-preserving. Using the rules that we have learned from any set of premises, it's possible to start moving step by step to other logical expressions, which, if the original premises are true, must also be true themselves, and therefore that argument is valid. This process is called syntactic calculus, and it's often written in the table form that we have learned. The first column shows which premises are supporting each step of our argument. The second column records a step number for reference. The third column is where we write out what we have derived at that step. And the fourth column shows the rule and the previous steps that we have used in making that derivation. In this example from last time, we proved that from a single premise P, we can derive that not P and not Q is false. But to do that, we need to assume the hypothesis that it is true and then show that this hypothesis contradicted our premise. But on to a couple of examples from real language. Look now at this simple argument, which is written in language that an ordinary person might use. We have to get to London tomorrow. We can either take the bus or the train. We really want to keep the cost down. The train is only cheaper than the bus if you book 2 weeks ahead, so we should take the bus. The form of this argument seems familiar. It looks like it describes a good plan, but is it valid? And if so, what is the syntactic sequence of this argument? Pause now if you want to have a go at that. By way of a hint, if you are concentrating on the text of the argument, then you may develop a much longer syntactic sequence and then find that it reduces to something simpler. Because that's what I did. And we'll explore that journey over the next few slides. I hope that it will be an instructive example, but we will be spending quite a lot of time on this simple argument. So if you are able to very quickly see what the final form will be, then good job. The first thing I did was to pull out some simple statements from the text of the argument, because it's really all we have to go on. Here are 6 statements that refer to how we get to London and which way is the cheapest. When I looked at the argument, 2 things stood out to me as really essential: that we must go tomorrow and that we will take the cheapest way to go. Tomorrow is less than 2 weeks away, so I started off with a conjunction of these statements as a premise, not W and C. I also used the disjunction B or T because we'll either take the bus or the train. We cannot take both. Our conclusion clearly is that we should take the bus, so this is a sequent. But is it valid? Well, it's difficult to see how we can infer one side of our disjunction from these 2 apparently unconnected premises, but we can do the truth table. And while we are here, let's get a little bit nerdy. Welcome to Excel. I love it here, or at least whenever I need to do anything with numbers, I do. But Excel also has basic logic functions built in, and you can use truth values as inputs in a cell. There are other ways to use computers to complete logic tables quickly. It is something they are very good at. The sequent we are looking at has 4 variables, and that means 2 to the power of 4 rows, or 16 rows in our truth table. We could still do this with a pen and paper, but that's a lot of T's and F's, and what if we just make 1 or 2 mistakes on all of those lines? So what we can do in Excel is lay out our variables in the table on the left, and then we can copy those columns into where they appear in the premises, or the opposite of that if we're using a negation. Great, now to get the answer, we're going to use the Excel formulas if, and, or. I will not tutorialize those here, I'll just point out the syntax that Excel uses as we go along. For the AND statement, not W and C, I tell Excel, if both of these cells are true, then give me true, otherwise give me false. And then for the disjunction B or T, I tell it, if either one of these rows is true, then give me true, otherwise give me false. We now have a truth value for each of our 2 premises. We can take the conjunction of those premises by using the AND formula again, and we now make the corresponding conditional with our conclusion to find out if the argument is valid. This uses the AND formula again, but we must be careful this time. Remember, the conditional is only false on one specific line, so that is the line we need to test for. So this time, I've told Excel, if the conjunction of the premises is true and the conclusion is false, then give me false, otherwise give me true. Looking down at the table, we can see that this argument is indeed invalid. Only on one line, as it turns out, but that is all it takes. Back to the drawing board. There are several of our statements that we still have not used. We need to somehow link the cheapness of the ticket with the way in which we will travel. This is probably going to need some conditionals. Since we will take the cheapest option, if the bus is cheapest, we will take it, and if the train is cheapest, we will take it. And we can include the timing of our journey by saying that if it is 2 weeks ahead, then the train is cheaper, and if it is not, then the bus is cheaper. This gives us 4 conditionals which describe contrasting situations where the bus and the train might be cheaper. At this point, I guessed that there should be some connection between the 2 cheapness statements and our intention to take the cheapest route, so I assumed that for us to take the cheapest route, A or S must be true. In other words, A or S is necessary for C. That now gives us a total of 7 premises comprised of 6 simple statements. 2 to the power of 6 means there will be 64 lines on this truth table. This is starting to get seriously unwieldy for a pen and paper table, but fortunately we have Excel. So, it's easy to include or remove as many premises as we want. Here is a truth table for our 7-premise sequence. It's really just a larger version of the simple one we saw above. The pattern for laying out the columns is the same, and I've put the letters in alphabetical order, even though the premises are not introduced that way. Again, it's worth noting how careful you need to be when trying to assign letters to premises and use them correctly, especially when we start to substitute sequence, as we shall see later in this video. For each premise, we can see that there are some lines which are true and some false. The corresponding conditional can only be false, and so the argument can only be made invalid if all of the premises are true together. Immediately, we can see that our output will be dominated by our primary requirement that not W and C are both true. This limits the 64 rows of our table down to just 16 possible rows, which could be true for all premises. Our other premises serve to filter out these rows until, looking at the conjunction of premises, there are only 3 rows where the conjunction of all premises is true, and all of these rows are in a section of the table where the conclusion B is also true. So our argument is valid. Now that we have shown that the argument is valid, we can ask ourselves, do we need all of those premises in order for it to be valid? Not W and C limits our outputs to just 16 lines, and only 8 of those would make the argument invalid. Do we really need 6 more premises to filter everything out? Fortunately, with the syntax of our Excel table, we can very easily remove a premise from the conjunction column and see what would happen to our argument without that premise there. So let's do that for all of our premises. Removing premise 1, our main premise, as we might expect, makes the argument invalid. Removing premise 2, though, has no effect on validity at all. Removing premise 3 makes the argument invalid, and the same with premise 4, we get an invalid argument. Moving on though, we can see that removing each of premises 5, 6 and 7 also does not make the argument invalid, although premise 5 does affect the table. So 4 out of our 7 premises, if removed, do not make our argument invalid. The next obvious step is to ask what happens if we remove all of those premises at once, and the argument is still valid. We can confirm that removing any one of the remaining 3 premises makes the argument invalid, and so our final sequence will include just these 3 premises. Not W and C, if not W then A, and if A then B. And now we can see that in fact this argument is just a slightly modified version of modus ponendo ponens. It doesn't even really depend on C at all. Asterisk, we have not W and this is sufficient for A. And if we have A, then this is sufficient for B. Therefore, B as a conclusion is a valid way to conclude this argument. We could even redefine W as it is less than 2 weeks until we travel, and our sequence is now syntactically the same as modus ponendo ponens. Any valid argument is a derivable sequent. And this sequence is easy to derive. It's just the same as an example from our last video. This is a simple example of how we can get from an argument in natural language to a derivation of that argument. And let us notice that even now this is a very oversimplified argument about travel. It ignores any other way we might get to London. It ignores that the bus or the train could be equally cheap and that we may have other reasons other than cost to prefer one way or the other. This shows us that although logic is a powerful thinking tool, it's not always a practical tool in everyday situations. So here then is the derivation that uses our 3 remaining premises. Notice that I have left C included, although the rest of the derivation requires only not W. There is a sense though in which C is needed, and we'll come back to that in a moment. You also may wonder why our other conditional premises are not necessary. For example, if S then T. This is because once we have not W, S is already off the table. It may be the case that if the train is cheaper, then we will take it, but as soon as we confirm not W, we can rule that out, and so we don't need it as a premise for the validity of our argument. However, we do still need C in a way. It is only because we will take the cheapest route that we can choose between the 2 types at all. In fact, we must in a way include 2 more premises to expand our derivation to account for this. Here is the expanded derivation, and we can see that we now use C and even more modus ponens to derive that if A then B, and therefore to our conclusion. I've also included premise 4 in which C also justifies if S then T, which it does. However, there's no relevance in this premise for the argument, so it can technically be removed in practice. Now let's take a look at another example from Newton's Smith, and it's even simpler than the last one. It is snowing, therefore either it is raining or it is not raining. Like our last argument, it is difficult to see how the premises can entail the conclusion. However, the conclusion takes the form of something that we have seen in an earlier bonus video. What is that? Well, the law of excluded middle, P or not P. Just to be cheeky here, let's assign the statement it is snowing with the letter R and the statement it is raining with the letter S. This is obviously counterintuitive, but it is absolutely okay for us to do this, and it's worth remembering that different people sometimes pick out letters in different ways. Let's look at the truth table for this simple argument. What do you think we will see? As you might have guessed, this argument is valid. The corresponding conditional is a tautology. This is because S or not S is always true. And this means there is a derivation for it using our syntactic rules. Pause now if you want to try that for yourself. And again, just a little hint, even though this argument is much simpler than the last, the derivation will end up being even longer than our last example. So our only premise is R, and we want to show that S or not S is true. With no connection to the premise, we'll need a hypothesis to try to get to our conclusion. We will assume the negation of our conclusion and try to work towards the negation introduction rule. However, this does not immediately give us anything to work with, so we must assume something else to get started. Let's assume one of these simple statements. Just assume S is true. This is starting a second subproof. But now we have S, we can use the disjunction introduction rule to bring in S or not S. This contradicts our first hypothesis, and so we can use conjunction introduction to show this contradiction. Side note, but you can see that the contradiction to write is quite long and could be tedious to do repeatedly in a derivation. So there is an additional symbol for a contradiction or falsehood, which is this upside down T symbol. We can use the rule and the previous lines to see exactly which statement is being contradicted. So with this contradiction, we are entitled to reject a premise. We can reject our second hypothesis, S, and now that we have not S, it's valid for us to use the disjunction introduction rule again to introduce S or not S. Careful, we are not reintroducing hypothesis S from line 3. We validly have not S, and we can use the disjunction introduction to introduce a disjunction with any other premise we like, and we are choosing S. But this now gives us S or not S again, which contradicts our first hypothesis. So we have exactly the same contradiction, which again enables us to reject a premise. This time we can reject our first hypothesis, premise 2. In step 9, we assert this negation, ending our second subproof, and we have demonstrated that the negation of our conclusion is false, so we conclude that it is indeed either raining or not raining, S or not S. The law of excluded middle reasserts itself. Hopefully you can follow why the last example is a tautology, but it might have struck you as a bit strange, and it absolutely is. First of all, the simple statement R is not used anywhere in the derivation, and we conclude with the law of excluded middle. Couldn't we do that with any initial premise or set of premises? Yeah, we absolutely could. As long as our conclusion is always true, it's not possible for the corresponding conditional to be false, and therefore that argument will be valid. This also shows us that there are plenty of valid arguments which will not be terribly useful for any practical purpose. But there's something else here. What if we don't even need the basic premise R to show S or not S? What if we were to start our argument at the second line? Imagine if we simply claim as a premise not P or not P. I mean, the law of excluded middle seems pretty dodgy, right? So let's negate it. Step 2, to start our derivation, we'll assume P as a hypothesis, and we can go through exactly the same set of steps. Introduce the disjunction, make a contradiction twice, and then get back to the law of excluded middle. But as we get there, we remove the support of our first hypothesis, which is the only premise in our argument. Our conclusion rests on no premises at all. If something can be derived from no premises in this way, then we call it a theorem. Theorems can be derived to rest on no premises. This is an unusual quality, but we're still working within the axioms, for example, the law of excluded middle itself, and we're using our established rules, so we're not just doing whatever we want here. But theorems have shown how some logical statements can appear to be more fundamental in deriving others. We can still write a theorem as a sequent. We do this by simply writing nothing on the left-hand side of the syntactic turnstile. So the law of excluded middle can be shown like this. Let's move on to look at something else we can do with our derivations. We can also substitute in sometimes whole sections of derivation that share the same syntax. We saw a few examples last time of arguments that have the same syntax, and it is fairly intuitive to think that if we can take one argument and then take out all of the letters and substitute in the letters of the second argument, that the same derivation would be valid again. It's important to be extremely careful when we do this, exchanging letters for other letters. It can be quite easy to mix up sentences and premises and end up with something that is absurd. So let's look at those arguments, and first of all, let me point out, in case you hadn't noticed, these are not serious arguments. Shocking, right? The first one is broadly true, but it all depends on what too much means. The second argument is clearly not sound as it is written, although I like to believe that logic is part of the answer to humanity's troubles. I don't want us to be robots. We can still disagree, but we can disagree more accurately and clearly than we do now. Right? But I'm getting off topic. Both of these arguments use modus ponens, which means they have a very simple form. Pause if you want now and write out these arguments using the letters above. The color coding helps to make the link quickly, but the first argument would look like this, and if we substitute P for Q and S for R, then we immediately have the second argument. We can say that both arguments are substitution cases of modus ponens. They are real-world examples of the same underlying form. Let's have a look at how we might introduce these ideas into our calculus, and apologies, I forgot to record this part on camera. Here we have a sequent that if P then Q entails that not P or Q. This makes sense. If P entails Q, then it must be true that we are either in a world in which not P is true, or in a world in which P is true, and so Q is also true. Note, this does not entail that if not P, then not Q. It is quite possible for both to be true, not P and Q. But since this derivation obviously depends on whether P is true or not, let us introduce the law of excluded middle. This is a theorem, and so we don't need to make it a premise. It is one of our axioms. But to include it in the calculus, we must cite it as a line, and then we record it as TI, a theorem introduction. Now we will divide our calculus to derive our conclusion from both sides of the disjunction. First, we assume P, and then we can use the conditional elimination to get to Q, and introduce the disjunction not P or Q. Great! On the other side, we assume not P, and this is even easier. We can introduce the disjunction immediately. We have now derived our conclusion from both sides of the law of excluded middle, and so we can move by disjunction elimination to the conclusion not based on either of those disjuncts. You can see that in this final step, we cite all of our premises, including the assumptions 3 and 6, and the two lines where we arrived at our independent conclusions. Here we have a very similar sequent. It is slightly longer than the first, but the form of our conclusion is still the same, and we can use that. If we take our first two premises, then we can use the conditional elimination to get to if B, then C. But now we have a substitution case of our last example. So our derivation will work again if we substitute B for P and C for Q. So we can cite SI, or sequent introduction, and then the sequent we are using to move to not B or C. We also cite the lines which we use as the, quote, premises of our sequent, although those do not become premises of our current argument. In this example, we cite only line 3, but our supporting premises are unchanged. This, of course, is just one way that you can record details like this in your syntactic calculus, and you might see other ways of doing similar things like theorem introduction and substitutions in other people's notations. So do watch out for that. I won't say any more about substitution right now, but again I want to warn you, it can be harder than you think to substitute correctly. It is fairly easy to do it with modus ponens above, but when your sequent might have 4 letters and 4 sets of nested brackets, or when you're taking a whole section of derivation from one argument and maybe pasting it into another, well, you can see how it might get confusing. Let me know if you want to look at some more examples of substitution cases in a further video. At this stage, let's go back and remind ourselves of the three rules that allow us to remove premises from an argument. This is usually done to help us close subproofs. The negation introduction rule removes whichever premise was negated. The conditional introduction replaces the antecedent premise with the introduced conditional instead. And the disjunction elimination will remove the two disjuncts as premises. This is one key way that arguments can proceed into a different form. There are an infinite number of possible derivations, and many of them are not that useful to us. When we do a derivation then, we try to arrive at a conclusion, usually one we've decided that we want to get to. There are strategies which help us move in certain directions, and I will introduce a few of those. But notice again how this shows that logic is a tool for exploring a space. It does not make value judgments. And I'm sorry if that proviso is getting boring over the course of this series. I think though some people want to hear it reinforced and other people need to hear it reinforced. So let's look at a few rules of thumb for maybe getting to a conclusion, and they will all be presented in the form of a conditional. Our first rule of thumb is, if the premises include a disjunction, then try to use the disjunction elimination rule, and you can prove your conclusion from each disjunct. You need to do this, otherwise that premise could lead to your conclusion being unfounded. Our second rule of thumb, if the conclusion is a conditional, then assume the antecedent as a premise and prove the consequent. This demonstrates the link between the two, and it justifies introducing that conditional. For our third rule, if the conclusion is a negation, then you can try and use the negation introduction by showing either the non-negated expression or its double negation to be inconsistent. For our next rule, if the conclusion is a conjunction, A and B, then you should try to prove A and B individually and then use the conjunction introduction rule. You must show that both of the conjuncts are valid to show that the conjunction of the two is valid. Moving on, if your goal is a disjunction, then you only need to prove one of the disjuncts and then you can use the disjunction introduction rule. This benefits from the versatility of the disjunction introduction to introduce any other premise, but do remember that that premise is not automatically validated except within that disjunction. If you want to rely on it further, you'll probably need to validate it with another premise. And then finally, if none of the above seem to help, or if your conclusion is a simple statement, then try assuming the negation of the conclusion and prove that it is a contradiction. There are other strategies you can use, of course, and if you do a lot of logic, you'll develop your own little shortcuts and little code substitutions for part of your logical calculus in getting from premises to conclusion. That is something to get you started though, and I hope you found it useful. In the next video, we're going to advance our syntactic logic by another level as we start to look at quantifier logic. Hi, hope you found that interesting. Like, comment, subscribe, etc. If you prefer shorter videos, you can find this cut up on our other channel just up there. But whatever you do, please keep learning something, because no matter who you are or how old you are, every day really is a school day. Bye for now.